Pluto is a distant and puzzling planet that was once a piece of our sun-based framework. However, recent disturbing claims by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning disclosure. They recommended that this frigid world may be on a possible impact course with Neptune. But how could this occur, and what may be the results of such an enormous event? Are we seeing an intriguing vast abnormality, or is there more to this approaching divine fiasco? Join us as we investigate the potential outcomes of a Pluto-Neptune impact. Pluto, a former planet now delegated a dwarf planet, remains a subject of interest and study in the vast universe. According to recent predictions by leading scientists, Pluto's orbit is hazardously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are raising concerns about a possible disastrous impact between these two heavenly bodies, which could pose a significant danger to Earth. But how is such an event even conceivable? Pluto's excursion around the Sun is dissimilar to that of any other planet in our solar system. It requires an astounding 248 years to complete a single orbit. Since its discovery in 1930, Pluto has not yet finished one full revolution. But the interest doesn't stop there. Pluto's orbit is characterized by its extremely elliptical shape, deviating substantially from the nearly circular orbits of the major planets. What makes Pluto's orbit even more surprising is its tilted nature, shifted by 17 degrees to the ecliptic plane. Pluto's orbital path is significantly more inclined compared to other planets. This inclination and eccentricity add layers of complexity to its orbital behavior. One of the most captivating aspects of Pluto's orbit is its convergence with Neptune's for about 20 years in each orbit. Pluto actually approaches the Sun closer than Neptune, challenging assumptions about their positions in the solar system. This prompts the inevitable question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational impacts of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers attempted to figure out its unique path. Unlike other planets, whose orbits lie mostly near the ecliptic plane, Pluto's orbit stands out due to its steep inclination and unusual shape. The mystery deepened with the realization that Pluto's orbit indeed crosses Neptune's. The stability of Pluto's orbit amid these complexities demonstrates the intricacies of celestial mechanics. The three-body problem in space involves determining how three objects, like Pluto, Neptune, and the Sun, move and influence one another with their gravity. It's akin to predicting their paths based on their initial positions and gravitational interactions. For Pluto, this issue highlights how its orbit, Neptune's orbit, and the Sun's gravity interact in a complex way. Terms like asynchronous libration, orbital precession, and VZK oscillation are crucial to understanding this phenomenon. Asynchronous libration, in Pluto and Neptune's case, means that when Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is vital in keeping their orbits from intersecting. Orbital precession refers to the upward movement of a body in its orbit. For Pluto, it ensures that when it comes closest to Neptune or any other giant planet, it is situated far above their orbital plane, providing an additional layer of protection against potential collisions. VZK oscillation, named after three researchers, Vladimir, Zelik, and Kai, who studied the movements of celestial bodies, describes how Pluto, Neptune, and the Sun interact gravitationally. This oscillation explains why Pluto's orbit near the Sun appears irregular. Despite Pluto's orbit seeming eccentric, this oscillation maintains its stability over extended periods. The VZK oscillation shows that, despite the apparent chaos in space, there are underlying patterns and rules that keep celestial systems intact. These factors ensure that Pluto's orbit remains stable, preventing it from crashing into Neptune or straying off course. This three-body problem is crucial to understanding how these orbits evolve due to gravitational interactions. Studying it provides insight into Pluto, our solar system, and even distant galaxies. Mathematical simulations in the late 1980s revealed that, despite these stabilizing factors, Pluto's orbit is inherently turbulent. Minor variations in initial conditions can lead to huge differences over centuries. However, these irregularities have been found to maintain stability over extraordinarily long timescales. Further research has shown how the giant planets, Neptune, Jupiter, and Saturn, influence Pluto's orbit. Neptune has a unique relationship with Pluto, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps keep Pluto's orbit stable. Moreover, Jupiter's massive gravitational influence plays a crucial role in stabilizing Pluto's path, with Saturn also contributing. These studies highlight how the gravitational exchange between Neptune, Jupiter, and Saturn ensures that Pluto stays on a consistent path for extended periods, possibly even billions of years. Without these stabilizing mechanisms, the solar system would be a far more chaotic place. Bodies like Pluto could crash into others or be ejected from their orbits, triggering a chain reaction with other celestial bodies. Understanding Pluto's orbit is crucial, especially when discussing the possibility of a future crash with Neptune. It provides a clearer picture of the dynamic nature of the solar system. Pluto's case demonstrates that even seemingly unstable orbits can reach a state of balance through the complex interplay of gravitational forces and orbital mechanics. This also underscores the importance of continuous observation and study of these phenomena to better understand our place in the universe. The concept of orbital chaos, which refers to the delicate dependence of a body's path on its initial conditions, is perfectly exemplified by Pluto. Even slight changes in Pluto's position or speed can dramatically alter its long-term orbit. Using computer simulations has been immensely helpful for researchers in understanding Pluto's movement. These simulations use advanced mathematics to model how Pluto and other celestial bodies like Neptune interact. By tweaking small details in the simulations, space scientists can see how minor changes can have a significant effect on Pluto's path. In the late 1980s, these simulations uncovered something intriguing about Pluto's orbit. Despite its stabilizing components, its path can still be highly sensitive to small disturbances, demonstrating the inherent unpredictability of celestial dynamics over vast timescales. This turbulent nature, however, doesn't necessarily mean that Pluto is at imminent risk of crashing into Neptune. The stabilizing mechanisms, such as asynchronous libration and orbital resonance, act as shields, ensuring that Pluto's orbit does not lead to catastrophic encounters within the foreseeable future. Why is a Pluto-Neptune crash impossible? The main reason a collision between Pluto and Neptune is unlikely lies in their orbital resonance. This 2:3 resonance ensures that for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This precise numerical relationship prevents the 2 bodies from ever getting too close to each other, as their positions are effectively locked in. While Pluto's orbit is chaotic on shorter timescales, the long-term stability provided by gravitational interactions between the major planets, particularly Neptune, Jupiter, and Saturn, ensures that Pluto's orbit remains stable over billions of years. These interactions create a delicate balance that prevents catastrophic events, such as a collision between Pluto and Neptune, from occurring. The fascinating aspect of this stability is that it results from the precise orbital resonance between Pluto and Neptune. The 2:3 resonance means that Pluto and Neptune will never be in the same place at the same time, thus preventing any direct collision. Their orbits remain intertwined in a predictable pattern, with each body maintaining a specific distance from the other, regardless of the seemingly irregular nature of Pluto's orbit. This cosmic choreography ensures that their paths continue without crossing. Additionally, the gravitational influence of Jupiter and Saturn plays a significant role in stabilizing the orbits of objects like Pluto. Jupiter's immense gravitational pull helps to steer Pluto's orbit into a more stable path, while Saturn contributes similarly by exerting its own gravitational influence. These massive planets, acting as cosmic stabilizers, help maintain the overall order and stability of the solar system. In conclusion, while the idea of a Pluto-Neptune collision might seem intriguing or even terrifying, the reality is that the complex gravitational interactions within the solar system make such an event incredibly unlikely. The delicate balance of orbital resonances, combined with the gravitational influence of the gas giants, ensures that Pluto's orbit remains stable. Rather than being on a collision course, Pluto and Neptune's paths are locked in a cosmic dance that has persisted for billions of years and will likely continue for many more. Understanding these interactions not only sheds light on the nature of our solar system, but also provides valuable insight into the dynamics of distant star systems and exoplanets. The study of orbital mechanics, particularly the three-body problem and resonance, continues to be a fundamental area of research in astronomy. By further exploring the complex relationships between celestial bodies, scientists can continue to refine our understanding of the forces that shape the universe and ensure the stability of planetary systems, including our own. In the end, while Pluto may no longer be considered a planet, its orbit and its relationship with Neptune provide a remarkable example of the intricacies and wonders of the cosmos and the dynamic forces that govern celestial bodies over vast timescales. The ongoing study of these phenomena ensures that we continue to expand our knowledge and appreciation of the universe and the delicate balances that make it a stable and harmonious system. Timescales, because of aversion to beginning circumstances, the general design is kept up with over cosmic periods. Anyway, researchers stay careful. These reproductions feature the significance of minute varieties, once in a while as little as a negligible part of a degree in tendency or a slight distinction in speed, which could intensify over millions of years. While a crash is far-fetched in the current era, incredible infinite time periods permit the chance of huge changes in the far-off future. Outcomes of a speculative crash. If a crash between Pluto and Neptune were to happen, the impacts would be fantastic, not only for the two planets, but potentially for the whole solar system. Such an event would release a huge amount of energy, potentially disturbing the orbits of neighboring celestial bodies. Debris from the crash could form a new asteroid belt, or even create a temporary ring system around Neptune. However, the Earth would likely remain unaffected given its distance from the event. The genuine results would be limited to the outer solar system, changing its dynamics and possibly impacting the Kuiper belt. Last contemplations. The possibility of a Pluto-Neptune impact captures the imagination, offering a dramatic perspective on the intricacies of celestial mechanics. However, current evidence suggests such an event is remarkably far-fetched due to the complex interplay of gravitational forces, orbital resonance, and stabilizing mechanisms. Still, the study of Pluto's orbit provides valuable insights into the broader workings of the solar system. By examining these distant worlds, researchers can better understand the delicate balance that keeps our planetary neighborhood stable. Whether as a planet or a dwarf planet, Pluto continues to intrigue and inspire, serving as a reminder of the captivating unpredictability of the universe. Starting with a small difference in where Pluto is or how fast it's moving, its orbit could look completely different after a few years. Despite this apparent chaos, Pluto's orbit remains stable over vast time spans, like billions of years. This stability implies that Pluto's journey around the Sun has a kind of order, even though it appears turbulent at first. Predicting celestial movements, especially those involving irregular orbits like Pluto's, is a colossal challenge. The inherent unpredictability of these systems means that long-term estimates are often filled with uncertainties. While mathematical models provide excellent tools for understanding and predicting the future movements of celestial bodies, they also highlight the limitations of our predictive capabilities. These models heavily rely on the accuracy of initial conditions, and any small error or distortion can lead to vastly different outcomes, making exact predictions an overwhelming task. The chaotic nature of planetary orbits, like Pluto's, reminds us of the ever-changing and dynamic nature of the universe. While we've made significant strides in understanding space, Pluto's case reminds us of how limited our knowledge of the universe still is. Grasping the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the wider dynamics of the solar system. It demonstrates how the presence and position of each planet can significantly influence the stability and trajectory of other bodies within the system. Concerns from leading astrophysicists. So, Why are leading astrophysicists recently raising concerns about a possible impact between Pluto and Neptune? Despite the intricate forces at play to prevent such an event, Neil deGrasse Tyson, an acclaimed astrophysicist and a key figure in promoting cosmology, offers a unique perspective on the mysteries of our solar system, particularly the fascinating case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, provides insightful analysis on the evolving understanding of celestial mechanics and the public's fascination with the outer reaches of space. Tyson's stance on Pluto's renaming is based on the ever-expanding knowledge of our solar system. He views the renaming not as a diminishment, but rather as a necessary adjustment to our growing understanding of the various bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continual learning and adaptation. He sees the complexities of orbits, like Pluto's, as a reminder of how much there is still to discover in space. This curiosity keeps the study of space exciting. However, despite Tyson's optimism, his thoughts on Pluto's potential crash with Neptune present a different picture. His concerns about the future of Pluto's orbit suggest that we may still have mysteries to uncover. Will Pluto collide with Neptune? Or is this just another moment of confusion in the ever-evolving universe of space? Only time and further research will tell. For now, we are left with a deeper curiosity about how little we truly know about our own solar system. Theoretical implications. The potential for a Pluto-Neptune collision raises profound questions about the dynamics of the solar system. It challenges our conventional understanding of planetary stability. That two celestial bodies with such vastly different characteristics could collide is both unsettling and captivating, especially considering the current relative stability of their orbits. Given that Pluto resides in the outer reaches of the solar system, far from the major planets, and Neptune is itself a gas giant with a strong gravitational field, the implications of such a collision would be immense for our understanding of gravitational interactions and the evolution of the solar system. To understand the dynamics of a potential impact, one must first consider the structure and properties of the two planets. Pluto, despite being a dwarf planet, contains various elements and compounds believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered in nitrogen ice, and it has an atmosphere primarily composed of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a gas giant, is composed mostly of hydrogen, helium, and other lighter elements with a deep, dense atmosphere. A collision between such disparate bodies would significantly affect their structure and behavior, potentially creating an event visible across vast distances. Gravitational interplay. What makes this hypothetical impact particularly fascinating is the influence of other planets and bodies in the solar system. While Neptune's gravity plays a dominant role in keeping Pluto's orbit stable, it is not the only factor at play. Jupiter, the largest planet in the solar system, also exerts a stabilizing effect on Pluto's orbit, preventing it from straying too far into Neptune's territory. Saturn's gravitational influence further complicates the dynamics of the outer solar system, making a catastrophic event between Pluto and Neptune highly unlikely. However, despite the apparent risks, ongoing research has shown that the interaction between Pluto and Neptune is not as simple as a clear crash course. The gravitational resonance between the two planets, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3, creates a kind of cosmic lock that prevents them from coming into direct contact. This resonance is a key reason why Pluto and Neptune's orbits, while intersecting in a vast field of space, have never resulted in a collision. Cosmic stability and resonance. This orbital resonance highlights the incredible intricacy of celestial mechanics. The precise interplay of gravitational forces ensures that Pluto and Neptune avoid catastrophic encounters despite their paths crossing in a three-dimensional cosmic arena. This delicate balance demonstrates the stability of the solar system, even in its most dynamic and seemingly chaotic regions. The resonance is not just a quirk of their orbits. It is a testament to the interconnectedness of all bodies in the solar system. Pluto's interactions with Neptune, Jupiter, and even smaller objects in the Kuiper Belt create a web of gravitational relationships that prevent disruptive events. Such dynamics illustrate the finely tuned nature of planetary systems and the profound forces that shape them over eons. The broader implications for planetary science. Understanding the mechanics of Pluto and Neptune's relationship offers more than just insights into their individual orbits. It provides a broader context for studying planetary formation, migration, and stability in other systems. Exoplanet research, for example, often reveals planets in tight or unstable configurations. By studying our own solar system stability, scientists can infer the conditions required for long-term equilibrium in exoplanetary systems. The stability of Pluto's orbit also sheds light on the Kuiper Belt, a region of icy bodies beyond Neptune. Pluto, as one of the largest and most studied objects in this region, serves as a proxy for understanding the formation and behavior of other Kuiper Belt objects. The gravitational dynamics of this region influence not only Pluto, but the distribution and behavior of countless smaller bodies. Challenges in predicting long-term orbital behavior. Despite our understanding of resonance and stability, predicting the exact long-term behavior of celestial bodies remains a challenge. Small perturbations, such as a passing asteroid or a minute shift in a planet's velocity, can have cascading effects over millions of years. This sensitivity to initial conditions, known as the butterfly effect, is a hallmark of chaotic systems. For Pluto, even a slight change in its velocity or position could alter its orbit over geological timescales. While current models suggest stability, the inherent unpredictability of chaotic systems means that new discoveries or changes in assumptions could shift our understanding. The human fascination with Pluto. Pluto has always captured human imagination, from its discovery in 1930 by Clyde Tombaugh to its reclassification as a dwarf planet in 2006. Its distant location, icy composition, and unique orbit make it a compelling object of study. The New Horizons mission in 2015 further deepened our understanding, revealing a surprisingly complex world with mountains, glaciers, and potential subsurface oceans. This fascination extends to its potential interactions with Neptune and the broader implications for the solar system. Hypothetical scenarios, such as a collision or a significant shift in its orbit, remind us of the fragility and dynamism of the cosmos. Looking ahead, the future of Pluto-Neptune dynamics. As technology and computational models advance, scientists will continue to refine their understanding of Pluto and Neptune's relationship. Observations from telescopes, data from spacecraft, and increasingly sophisticated simulations will shed light on the long-term evolution of their orbits. While a collision remains unlikely, the study of such hypothetical scenarios is valuable. It forces scientists to consider extreme possibilities, test their models, and improve their understanding of celestial mechanics. These efforts not only deepen our knowledge of Pluto and Neptune, but also enhance our ability to study other planetary systems. In the end, the story of Pluto and Neptune is a testament to the wonders of the universe. Their intricate dance, governed by gravity and resonance, reminds us of the beauty and complexity of the cosmos. Whether as a planet or a dwarf planet, Pluto continues to inspire curiosity and wonder, serving as a window into the ever-changing nature of our solar system.